about numerical integration. In numerical integration, we carry out integration over a set of discrete points. Unlike analytical integration, we do not have a function y that is equal to f of x here. So what we do is that we first take these discrete points xi, yi, where I goes from 0, 1, 2 up to n, and as a first step we fit a polynomial y that is f of x. Now to do so, in this case here I am showing this is Lagrange polynomial, but you can use any other method to fit a polynomial. And after we fit the polynomial, you see that in Lagrange polynomial there are two parts. One is this f of xi and another is this x minus xj divided by xi minus xj. When I integrate this function y over certain interval x0 to xn, this fxi parts are constant, so they come out of integration. The remaining part has an x into it, so the remaining part is a function of x. When I integrate it and apply the limits x0 and xn in this case, what I have is certain constant, that is, let's say ai. So at the end of my integration will be a result of the linear combination of f of xi, and f of xi are the points that are given here to begin with. Unlike analytical integration, numerical integration is always definite integral. We cannot have an analytical expression as we have in analytical integration. When you conduct numerical integration using some of the scientific computing tools such as, let's say, SciPy in Python, and you get the integration result as a function, don't get confused by that. The integration result is always a real number and the function is simply a polynomial interpolation over those real numbers. That is how by default the SciPy, for instance, plot the results. But the integration is always in the form of a real number. There are several techniques for conducting numerical integration. The first in this lot is something that we call trapezoidal rule. In trapezoidal rule, we take this polynomial as simply as a straight line, and let's see that how we do that. Let us say that we have a function that is y is equal to f of x, which is shown by this blue line here. And then I have 2 points over this function x0, y0 and x1, y1, which are these red dots here. We are interested to evaluate integral y dx between x0 and x1. Why do you need to do that numerically? Numerical integration are usually necessary when we have only the discrete points xi, ui, and we really don't know anything about the underlying function that is probably generating this yi's. But in this case, if we know y equals fx, can't we do an analytical integration? Now we know that for many functions the analytical integrations are absolutely difficult, and sometimes it is just not possible. When I say it's not possible, maybe it is not possible for me, I cannot integrate that particular function, or maybe that function is such that nobody can have an analytical integration. Both way we have to go for numerical estimation of the integration, and when we do numerical estimation we only do a definite integral, not an indefinite integral. So as we discussed, the general approach will be whatever the discrete points we have. For instance, in this case we have discrete points x0, y0 and x1, y1. General approach will be to fit our best polynomial between these 2 points and then integrate the polynomial. So in this case, since we have only 2 points, so best we can do is the linear fit, and that's the simplest case of all numerical integration. And in a linear fit, we can write in terms of a Lagrange polynomial. This is of course a general expression of Lagrange polynomial. When we take a Lagrange polynomial, these LI's are the functions of x, and we write Li as a product of j going to 0 to n, x minus xj divided by xi minus xj, and j cannot be equal to I. When I have only 2 points, this n becomes 1. The remaining part is just the same, x minus xj, xi minus xj. Since I have only 2 points, my I can go only from 0 to 1. That means I have only 2L. If I take, for instance, L naught, I write this is product j equal to 0 to n, and of course n equal to 1, x minus xj divided by x naught minus xj. I simply put a 0 in place of I. Now I have to take this product. In this product, j can go from 0 to 1, but since I equals 0, j cannot take the value of I, so j cannot be 0, which means j can only be 1, which means that my L naught is x minus x1 divided by x naught minus x1. We can do this exercise once again, and let us say we have L1, and in case of L1, once again we have the same expression, j equals 0 to n. Here n equals 1, and this 1 we have replaced I here, so I have x minus xj, x1 minus xj. Now we want to take this product. This product goes from j equal to 0 to n. Here I equals 1, so j cannot be equal to 1, so the only option is j will be 0. So I have x minus x0, x1 minus x0, and thus this Li fxi is given by L naught fx naught plus L1 fx1, and this L naught and L1, we have the expressions now available. Now with this expression of y as a straight line, and with this given L naught and L1, we want to find the integration y dx x naught to x1. We start by putting this expression L naught fx naught plus L1 fx1 in place of y. Fx naught is simply a constant. This is the value of this function y equals fx at x equals x naught. So this is simply a real number in general, so that's a constant. It comes out of integration sign. Inside the integration sign we have L naught x dx, and the integration goes from x naught to x1. Similarly, in the second term, fx1 is a constant. This is the value of y at x equal to x1, so it comes out of integration sign, and I have the integration x naught to x1 L1x dx. I can now write the expression of L naught and L1 inside this integration sign, and now all I have to do is that I have to integrate x minus x1 divided by x naught minus x1, and x minus x naught divided by x1 minus x naught. So this is very simple. So I have this x minus x1 whole square divided by 2 multiplied by x naught minus x1, and the second term is x minus x naught whole square divided by 2 multiplied by x1 minus x naught. The limits are x naught and x1. If I apply these limits here, I can simplify this term within the third bracket, and when I do so, I get at the end this is x1 minus x naught divided by 2 multiplied by fx naught plus fx1. Of course, this fx0 and fx1 are simply y0 and y1, and y0 and y1 you can see that in this figure this is y0 will be AD and y1 will be this BC. So when I have this x1 minus x0 by 2, x1 minus x0 is this CD. So x1 minus x0 by 2 and multiplied by y0 plus y1, this is essentially the area of this trapezium ABCD, and this area of this trapezium is the approximation of the integral y dx. Because this is the area of the trapezium, we call this the trapezoidal rule. Now we can see that as I fit the trapezium in this curve y equals fx, the actual integral should have been the area below this integral y equals fx. As I am taking the trapezium, I am missing out some part of it, and this could be significant, and this is my error in numerical integration. I was supposed to integrate y dx, but instead I have integrated p dx, where p is a polynomial in general, but in this case this is a polynomial of degree 1, which in this case is a straight line. And I have seen that the evaluation of this integral is x1 minus x0 by 2 multiplied by y0 plus y1, which is the value will be I. This is simply a real number because this is a definite integral, and certainly from the figure we can see that it is not same as y dx, so there is an error. Now recall our discussion on errors in Lagrange polynomial interpolation, and in that case the error was fx minus px, that is the error term, and error term was given by whatever the function we are fitting the polynomial, that function n plus 1th derivative of that. The value of this derivative is taken between this point x0 and x1, which is some point xi, and we want to take this value where this fn plus 1 will be maximum, divided by n plus 1 factorial and multiplied by the product x minus xi for I going to 0 to n. Now in case of this integral, we can clearly say that, well, if I integrate this polynomial I get I, and if I integrate this fx, that is simply the integral of x0 to x1 y dx, this is the integral of fx, which will be equal to integral of polynomial, that is the I, and then I integrate the error term. When I integrate the error term, this is a definite integral from x0 to x1. N is 1 here, therefore this n plus 1 factorial will be 2, so I have a 1 by 2 here. Since n plus 1 is 2, I have double prime m at certain point xi, and I want to take this point such that this f double prime xi is the maximum value in that interval, and then the product x minus xi is x minus x0, x minus x1, integral of this entire term dx. So I can take this f double prime outside because I'm only taking this xi wherever the double integral will be maximum, and I'm integrating this x minus x0, x minus x1. If I do so, then you will quickly see that I apply this limit here, I'll get this h cube by 12 f double prime xi, where this h is simply the x1 minus x0. This is called either the step size, or this is also called a grid size. Therefore, integral y dx, I can say that this is this I, this part is of course I, and then there is an error term. The error term is given by the cube of the step size and double prime of this particular function y equals fx, if we know the function. you have to understand that for many cases in numerical integration, the function by itself is not known to us, so we cannot calculate this error term with certainty, but we do know that this error term will be of the order of h cube, and by order we means that how this error term will behave as we change h. So we expect that if we, for instance, make h twice, then the order of error is, since it is h cube, so if h goes from h to twice h, we believe that the order will be 8 times, probably the error will be 8 times. And when we have relations like this, we call this is a third order accurate scheme. So trapezoidal method is third order accurate since the error is of the order of h to the power 3. Of course, you understand that if f is, for instance, linear, then f double prime will be 0 everywhere, and in that case the error does not depend on h at all. So the phrase third order accurate does not make much sense if f is linear. In fact, the evaluation of this integral will be exact no matter what is the value of h, or you can say that error will be always 0 since f double prime is 0. Now, since error depends on h, we want to take small h, and to do so, for almost all practical cases, we don't use the simple trapezoidal rule that I have just shown. What we do is something that we call is a composite trapezoidal rule. And what does it do? In composite trapezoidal rule, we divide the integration interval. So in this case, we are interested to carry out an integration of function y between interval x0 to xn, and I divide this domain into many small segments. So for example, I have this x0 to x1, so I have x0 here, and then I have x1 here, and first I conduct a trapezoidal rule integration within this x0 to x1 region. Then I have another trapezoidal integration between x1 to, let's say, this is my x2 here. Then I conduct between x2 and x3 here. This is how I make many segments, and I calculate the area of each segment, and then I add up all the areas. That is how in practice we conduct numerical integration. So here I have x0 to x1 y dx, then again x1 to x2 y dx, etc, etc. In general, xi to xi plus 1 y dx, and at the end I have xn minus 1 to xn y dx. So if I assume in this case, just for the sake of simplicity, that the grid size is uniform, which means that this xn minus 1 is equal to xn minus 1 minus xn minus 2, etc, etc, is equal to x1 minus x0. So all these intervals are uniform, and I say this is my step size or grid size, that is h. In integration we usually use this term step size. In differentiation we call it grid size. So they essentially mean the same thing. So I take it to be uniform here, and with this uniform grid size Let us say that I am going between xi to xi plus 1 and I am taking this y dx. Numerically this will be equal to h by 2 multiplied by yi plus 1 and I have an error of the order of h to the power 3. So when I take the integral x0 to xn y dx, it will be summation of all such terms. That means h by 2 multiplied by y0 plus y1 plus h by 2 multiplied by y1 plus y2, etc., all the way up to h by 2 multiplied by yn minus 1 plus yn plus n multiplied by some error, which is, we know that, of the order of h cubed. So the errors are adding up. So now I can take all this term together. I can take h by 2 and I write y naught plus 2y1, 2y3, 2, etc., up to 2yn minus 1 plus yn. And in the error term I have n, and I know that n will be the xn minus x0 divided by h. N is essentially the number of intervals that we have. So this many intervals we have, and since I have h here and I have h cube in the error term, when I multiply it, my error will be of the order of h square. So this is a second order accurate scheme. But we should not worry about the accuracies becoming smaller. Accuracy is actually still very good. It was earlier third order, now it is second order. But as we go from single step to composite, what we are having, this h is much smaller than the single step. Because the h is small, the order of error being h square is not a disadvantage. So now we can summarize the trapezoidal rule. Here you have y dx between x0 to xn equals h by 2 multiplied by y0 plus 2y1 plus 2y2 up to 2yn minus 1 plus yn, and we have an error of the order of h square. So when I take it locally, trapezoidal rule is third order accurate. When I take it globally, trapezoidal rule is second order accurate. So within an individual segment, the integration is third order accurate, but when I add many of such segments, the integration becomes second order accurate. But you have to understand that when taking one step to many steps composite gives a smaller step size, so overall the error will reduce. While the error is reducing or not, you can test that in an exercise here. So let us say that we want to use trapezoidal rule to evaluate 0 to pi sin x dx. And when you do so, you try to repeat this exercise for n going to 10, 50, 100 for different n. By n, I mean that you go from x0 to xn or x1 to xn plus 1. How you give this index, that is up to you, and if you are writing a computer program, then depending on the programming language, they start an array with a default index. The default is 0 in some language, in C family of language. So if you are using C, Python type language, then the default is 0. In Fortran family of language, the default is 1. So in Fortran, or if you are using Octave or Julia, you will have this array will start from default will start from 1. But of course you can set this default in any language. You can set the index by your own. I am only talking about the default, and in this course, of course, so far I am going with this default to be 0, but later on I'll show you also the default 1. You have to be familiar with both these defaults if you want to have a career in numerical area. So when you conduct this integration sin x dx over 0 to pi, if you do a manual calculation by yourself, or if you write a computer program using only primitive operations, you will get only real numbers. If you conduct this using the trapezoidal routine, in for instance in SciPy, you will see that your results will be an array, and when you plot it, it will plot a polynomial. That is essentially plotting this this particular integral for all this starting from x0 to x1 to x2 for all these limits. So it is plotting, actually it is giving you the array is coming from 0 to this h sin x dx. Then the second term in the array is 0 to 2h sin x dx, etc, etc. This is how it is generating an array. So if you are getting an array, don't get confused. The definite integral is always a real number, but if you are using some sort of a black box type routine, then it may be giving you all these numbers just by changing the upper limit, and that is how you are getting the array. So I'll request you to conduct this numerical experiment and see that when we change n, how the error is changing. So that's all for this lecture. Thank you, and I'll see you in next class.